Engineering ASMR, Episode 1, Three-Phase Power. Three-phase electric power is a common type of alternating current. It's used in electricity generation, transmission, and distribution. It is a type of polyphase system employing 3 wires and is the most common method used by electrical grids worldwide to transfer power. In three-phase power, the voltage on each wire is 120 degrees phase shifted relative to each of the other wires. AC systems allow the voltages to be easily stepped up using transformers to high voltage for transmission and back down for distribution, giving high efficiency. A 3-wire three-phase circuit is often more economical than an equivalent 2-wire single-phase circuit. At the same line to ground voltage, the three-phase system uses less conductor material to transmit a given amount of electrical power. In a symmetric three-phase power supply system, 3 conductors each carry an alternating current of the same frequency and voltage amplitude relative to a common reference. However, with a phase difference of 1/3 of a cycle between each. That phase shift is 120 degrees. The common reference is connected to ground, and often to a current-carrying conductor called the neutral. Due to the phase difference, the voltage on any conductor reaches its peak at 1/3 of a cycle. The phase delay gives constant power transfer to a balanced linear load. It also makes it possible to produce a rotating magnetic field in an electric motor and generate other phase arrangements using transformers. For instance, a 2-phase system using a Scott-T transformer. The amplitude of the voltage difference between 2 phases is the square root of 3, or 1.732, times the amplitude of the voltage of the individual phases. In a 3-phase system feeding a balanced and linear load, the sum of the instantaneous currents of the 3 conductors is 0. In other words, the current in each conductor is equal in magnitude to the sum of the currents in the other 2, but with the opposite sign. The return path for the current in any phase conductor is the other 2 phase conductors. Constant power transfer and canceling phase currents are possible with any number of phases. Of course, maintaining the capacity to conductor material ratio that is twice that of single-phase power. However, 2 phases result in a less smooth current to the load. 3-phase systems may have a 4th wire, common in low-voltage distribution. This is the neutral wire. The neutral allows 3 separate single-phase supplies to be provided at a constant voltage and is commonly used for supplying multiple single-phase loads. At the power station, an electrical generator converts mechanical power into a set of 3 AC electric currents, one from each coil or winding of the generator. The windings are arranged such that the currents are at the same frequency, but with the peaks and troughs of their waveforms offset to provide 3 complementary currents with a phase separation of 1/3 cycle. The generator frequency is 60 Hz in America. In other parts of the ninja world, such as Europe, the frequency is typically 50 Hz. At the power station, transformers change the voltage from generators to a level suitable for transmission in order to minimize losses. After further voltage conversions in the transmission network, the voltage is finally transformed to the standard utilization before power is supplied to customers. Anyone from the Hidden Leaf Village already knows that most automotive alternators generate 3-phase AC and rectify it to DC with a diode bridge. A bridge rectifier uses 4 diodes to reverse the direction of both sides of the AC pulse. With a bridge rectifier, the DC still oscillates from 0 to a peak value, but it doesn't cut out half the time. There are two types of transformers ninja engineers use. A delta-connected transformer winding is connected between phases of a three-phase system. A Y transformer connects each winding from a phase wire to a common neutral point. In an open delta, only two transformers are used. A closed delta made of three single-phase transformers can operate as an open delta if one of the transformers has failed or needs to be removed. In open delta, each transformer must carry current for its respective phases and for the third phase. Where a delta-fed system must be grounded for detection of stray current to ground or protection from surge voltages. A grounding transformer may be connected to allow ground fault currents to return from any phase to ground. To restate, here are two basic three-phase configurations, Y and delta. A delta configuration requires only 3 wires for transmission, but a Y configuration may have a 4th wire. The 4th wire, if present, is provided as a neutral and is normally grounded. For those who do not possess the visual powers of the Uchiha, here is a simple tip to tell Y and delta apart. A Y configuration looks like the letter Y. Delta, however, looks like a triangle. The 3-wire and 4-wire designations do not count the ground wire present above many transmission lines, which is solely for fault protection and does not carry current under normal use. A 4-wire system with symmetrical voltages between phase and neutral is obtained when the neutral wire is connected to the common star point of all supply windings. In such a system, all 3 phases will have the same magnitude of voltage relative to the neutral. The 4-wire Y system is used when a mixture of single-phase and 3-phase loads are to be served, such as mixed lighting and motor loads. An example of application is local distribution in Europe and elsewhere, where each customer may be only fed from one phase and the neutral. Electrical engineers try to design the 3-phase power system for any one location so that the power drawn from each of 3 phases is the same. As far as possible at that site, electrical engineers also try to arrange the distribution network so the loads are balanced as much as possible. Generally, there are 4 different types of 3-phase transformer winding connections for transmission and distribution purposes, based on Y and delta connection. The 4 are as follows. Y to Y is used for small current and high voltage. Delta to delta is used for large currents and low voltages. Delta to Y is used for step-up transformers. Y to delta is for step-down transformers. In the perfectly balanced case, all 3 lines share equivalent loads. Examining the circuits, we can derive relationships between line voltage and current, and load voltage and current for Y and delta connected loads. In a balanced system, each line will produce equal voltage magnitudes at phase angles equally spaced from each other. Let's consider V1 as our reference and VLN to be the voltage between the line and the neutral. Using angle notation, we get the following equations. V1 equals VLN angle 0 degrees, V2 equals VLN angle negative 120 degrees, V3 equals VLN angle positive 120 degrees. These voltages feed into either a Y or delta connection. When the currents on the 3 live wires of a 3-phase system are not equal or are not at an exact 120-degree phase angle, the power loss is greater than for a perfectly balanced system. The method of symmetrical components is used to analyze unbalanced systems. An important class of 3-phase load is the electric motor. A 3-phase induction motor has a simple design, inherently high starting torque and high efficiency. Such motors are applied in industry for many applications. A 3-phase motor is more compact and less costly than a single-phase motor of the same voltage class and rating. And single-phase AC motors above 10 horsepower are uncommon. Three-phase motors also last longer than single-phase motors of the same power used under the same conditions. This concludes the introductory lecture to three-phase AC power. Thank you for listening. Electrical engineering is a strong passion for all of us ninjas.